in some of these variables here to evaluate the models. Of course, when you go back in the past, it's more and more difficult because you have fewer and fewer data. You can do that for maybe internal variability, but external variability in chlorophyll, you have only 15 years of data, satellite observations. It's not enough to look at external variability. And another point of difficulty is the fact that the Earth system models, they generate their own climate. And so the internal variability in the data and in the ESM, in the Earth system model, are not in phase. So the climate model will generate its own El Niños, La Niñas. So you cannot say, let's look at 97 in the data and 97 in the model, because of course there is no reason why the model would have an El Niño in 97. So you have to find clever ways to compare internal variability as observed and as simulated by the ESMs. And then another way to evaluate the models is to turn to longer time scales and use the paleo data records. And of course that's also very difficult because those data are very sparse and usually indirect, so it's only proxies of some of the variables that you simulate. And of course the simulations also are sometimes very complete because you don't have a complete understanding of all the forcings on different variables. So I will illustrate evaluation of Earth system models with two techniques here, one using internal variability and another one using some longer time scales with valuable data records. So that's based on two papers here. So the first one is basically using something that is very well known. It's the variability of primary productivity as observed by, or as seen by the satellites, and for example by Berenfeld in 2006. And Berenfeld was showing this clear correlation between anomalies in NPP, in gray here, from 1997 to 2006, and anomalies of stratification in the tropical ocean here in red. So you have here a clear El Niño signal, low productivity, and a stratified tropical ocean. And you have here the La Niña times, if you want, with a positive NPP anomaly, and so here the axis is in reverse order, and with the destratification of the tropical ocean. So in your ESL, you cannot compare these events, but you can compare the statistical relationship between some physical drivers and the response of marine biogeochemistry. So that's what we've done with the IPSL piskless global models. And you have here the relation between this stratification index and the anomalies of NPP in the tropical ocean, 40 south to 40 north, as seen by the data in black from 1997 to 2005, and as simulated by your model here in red. And you see that even if the model is not reproducing high El Niño events like the ones that have been observed in 1997, the relation between changes in NPP and changes in stratification here are quite well reproduced by the model. So that's the way you can use internal variability as observed here by satellites and your model to do some evaluation. And even at the local scale, that's a correlation map, local NPP versus the stratification index, so some global value here. That's from the satellite observations, and that's from the model. So you see that you find the same kind of big dipoles with when you go into an El Niño events. You have less productivity here, but more productivity in the Eastern Indian and the Western Pacific here, and that's partly produced by the model. So we can look at global diagnostics here, but also at the local scale. Another way to evaluate the models is to turn to the past. And here we've used the centennial variability of productivity as recorded by sediment core. So for that we've focused on some specific events that are called IMBEC events. I don't know if all of you know what's an IMBEC events. So those events have been recorded in the past 100 kilometers here, so that's the present time. You go to the past on the left here. And in the North Atlantic, the sediment cores of the North Atlantic, we have 6 times very high percentage of detrital carbonates. And we think, or the paleoceanographers, they think that these detritus have been brought here by big iceberg discharges. So these events here, IMBEC events, are linked to iceberg discharges in the North Atlantic. And they are recorded also in all the climate records of the Northern Hemisphere. So after these IMBEC events in the North Atlantic, you have a very strong cooling of Europe, modification of the circulation in the North Atlantic. So those are big events taking place of maybe a few hundreds of timescales may be relevant to what we will be seeing in the next decades and centuries. But few informations on biogeochemical cycles on these events. That's the information that have been gathered here. From 40 segment cores, you have modifications of productivity, and you have some clear signal. In the North Atlantic, most of the cores clearly say that after an anaerobic events, you have a decrease in productivity, maybe an increase in productivity in the Southern Ocean here, and less productivity in the North Pacific, Indian Ocean. So that's very qualitative, but it gives you some response to those big climate events in terms of marine productivity. So we run the model basically simulating an idealized IMBEC events here, and then you can compare qualitatively the changes in MPP that respond to IMBEC events and the gathered information here. And you see that in the North Atlantic, if you bring lots of fresh water, you will change the stratification and you will decrease MPP as the sediment cores will tell you. In the Southern Ocean, it's a bit more patchy here, but you have also this seesaw, this dipole between the North Atlantic and the Southern Ocean that is reproduced by the model. Indian Ocean, North Pacific, maybe the model is also reproducing part of the changes that are observed. So that's the start of those kind of things, but it's a way to evaluate the models in different climates, long time scales, maybe more relevant to centennial changes that we will see. Okay, that was the first part. Now I turn to climate change impact on marine productivity. So the first kind of results that were obtained on that topic were using very simple models. That's the one I was mentioning in the beginning, geochemical model, only export production, and in very idealized scenarios. So you have PCO2 here increasing from maybe 350 to almost 700 in 70 years, 1% per year, and SST is responding, clear warming here of the surface ocean, and that's the delta production, so changes in MPP. And so that was published more than 10 years ago. And basically the three models that we were using at the time were all simulating a decreasing global MPP in response to climate change. The interesting story maybe at the time was this strong opposition between the low latitudes that respond to climate change by decreasing export production or even primary productivity, and the high latitudes here in the North Pacific and in the Southern Ocean responding to climate change by increasing productivity over a time scale of something like 100 years. So global decrease, -5 to -10%, but a strong opposition between low and mid latitudes that you can see here on the zonal mean. So the changes in export production from 2 times CO2 minus 1 times CO2, 5 different models here, plus 30% and minus 20%. So significant and big changes in MPP responding in response to climate change. So now, so that was 10 years ago. Now, if you turn to the new generation of couple models, so the CELIC5 generation, and here I plot the changes in MPP in relative units from 2005 to 2100 in the RCP 8.5 scenario, which is the high-end scenario. And I have, I think, 8 models here. We will have more than that very soon, but at the time we had 8 models here. And you see that all models, they predict or they project a decrease of MPP with climate change. Of course, some differences here in 2100, but you have a global decrease of MPP by -5 to almost 20% in 2100. So very similar to what was obtained with much simpler models 10 years ago. If you look at the regional distribution of those changes in MPP, you have again increasing MPP in red, decreasing MPP in blue, and that's the changes from 2005 to 2100, and that's an ensemble model mean. So I've basically averaged the 8 models here, and the hatched regions that you have here, that's the black dots here, they tell you when more than 75% of the models agree on the sign of change. So it gives you like a measure of the confidence or on the uncertainty you have on your model projections. And you have some clear signals here in those maps with a large decrease in productivity in the North Atlantic simulated by all the models. In all the models also you have a clear decrease in MPP in the tropical oceans. And in all the models also you have an increasing MPP in the Southern Ocean, here close to the Antarctic continent, but also here between 45 and 50 stars. So again, new models, more complex in terms of biogeochemistry, new climate models. We still have these large regional contrasts with decrease in NPP up to minus 50% in the North Atlantic, decrease in the tropics, and increase in the Southern Ocean. You have also regions where the models just don't agree. It's the case in the Arctic that I haven't shown here. You have half of the models saying more NPP and half of the models saying less NPP. So, of course, there are clear regions where we don't understand anything.
They all have dynamic tides?
Sorry?
They all have dynamic tides?
They all have dynamic tides.
Laura, can you also explain the reasons of this increases or decreases?
Yes.
Maybe not all students know.
I come to that.
Okay.
Another interesting thing is to compare this new intercomparison to what was published in 2011 with the previous generation of models. So we had at that time 5 models. So you have no common models between those two maps. And still you see some very similar patterns here, large decrease in the North Atlantic, in the tropical oceans here, and increase in the Southern Ocean. So this new semi-5 model class, if you want, give, in terms of changes in NPP in response to climate change, very similar results to previous model intercomparison study. So now I come to maybe the mechanism. So we can explain this in a very simple way, this contrast between low latitudes and low and mid latitudes and high latitudes. So in low latitudes, where NPP is mostly limited by the availability of nutrients in the water, climate change will drive a strong stratification of the ocean because you warm the surface of the water, so you decrease density, and you end up with more stratification. And if you have more stratification, you have less nutrient coming from below, and because of reduced mixing, lower nutrient supply, you decrease plankton biomass and productivity in the surface ocean. So that's what's happening in the North Atlantic and in the tropical oceans in all the models that we've looked at so far. At higher latitudes, in the Southern Ocean, and in some models in the Arctic Ocean, you have more productivity, and that's basically because in those regions, productivity must be light limited. So if you melt the sea ice, you have more light, and of course, if you stratify the ocean, if you reduce the mixing, you will have an increase in plankton in the eliminated surface waters that will drive more productivity. So you may have the same physical driver, stratification, with different outcome depending on the regions where this is at.
Why did they increase the subsurface water in the tropics?
So what I've shown was integrated NPP before. So this would encompass all the subsurface and surface. Of course, what we have, so we have things, interesting things. You may have, so yeah, if I come back here, so that's just NPP. But if you look at chlorophyll, the distribution on the vertical of chlorophyll, of biomasses, you have very interesting things depending on the regions you look at. For example, what we have here in those models is an extension of the oligotrophic gyres. You have also a deepening of the subsurface chlorophyll maximum here in the oligotrophic gyres. So that's only an integrated view, 2D, but you can really look at the 3D and you have some very similar results by the different models. Yeah.
Why not consider the horizontal advection?
Sorry?
Why not consider the horizontal?
We consider also the horizontal, of course. So this can play a role. But the first order, from what we've looked at, so then it depends on the region. If you go in an upwelling regions, it's not the vertical mixing, it will be really the upwelling intensity that will drive. So it's really advection that will drive the changes in nutrient delivery. In the North Atlantic, it seems that really it's almost a 1D process, vertical mixing. But of course, advection will play a role. And in all those models, so we have them embedded in OGCM, so we have, of course, vertical advection, horizontal advection, and everything. Okay, just another point. I've shown you that those models can represent different phytoplankton groups. So we've started to look at the changes in the ratio between the different phytoplankton functional groups that we have. And here, that's French, sorry. We have the impact of climate change on phytoplankton communities using the Pisces model I was showing you before. And in blue, it means that you have a reduction of the relative proportion of diatoms compared to the small phytoplankton. So what the models, not only Pisces but some other models, tell us is also that with climate change you have They need more small cells and less of the